All right, in this video we're going to talk about electron filling order and spend some time thinking about how it specifically applies to the D block and where some interesting things start happening. Now, when we're thinking about filling electrons and electron configuration, there's quite a few different terms that come up. And the first one is going to be that of the Aufbau principle, which tells us about building up our electron configurations. All the Aufbau principle tells us about is that we can't add electrons into a higher shell until the lower shell is completely full. So, for example, we have to put in all of our n equals 1 before we can go on to n equal 2. So that'll be an important part of this. Next rule that we have is that of Hund's rule, which tells us about how electrons can pair up. So we just talked about being in 1 versus 2, and now we're going to be saying, let's look, for example, within 2. 2, we could have 2s, we can have 2p. And let's just specifically look at the 3p orbitals within 2. So when we're looking at Hund's rule says when we go to fill in our electrons, when we have the choice between pairing up electrons or putting them into separate orbitals, we want to put them in separate orbitals. The only time we will add and pair up our electrons is when we are absolutely forced to. So, for example, if I put 4 electrons in here, I would have to have that 4th one being paired up now. Doing this will minimize electron repulsions, leading to an overall lower energy system. Last bit that we're going to have here is the Pauli exclusion principle. This one goes back to our connection with quantum numbers for a minute, and we said that with quantum numbers, each one told us a specific address. So, for example, we could have an electron that was n equal 3, l equal 2, ml equals 0, and ms equals plus a half. Now, what Pauli said here is that when we're dealing with electrons, only one electron can have those 4 quantum numbers. You will not be able within an atom to find a second electron that has those same 4 quantum numbers. One of them always has to be different. So that's what Pauli exclusion says, is that all 4 quantum numbers for an electron must be unique. Now that we have that, we can start thinking about how electrons will actually be added to an atom. And there are 2 different cases, but we're really only going to care about one for the most part. We have the hydrogen-like species, meaning these are all 1 electron systems. So this would be hydrogen, this would be helium plus, this would be lithium 2 plus, so on and so forth. These are all 1 electron species. And that's not all that useful in many cases. Really, where we're going to spend most of our time is thinking about multi-electron species. And what we're showing here is the electron orbital energy diagram. So, going along with the Aufbau principle, we see that our first level is going to be the 1s. And we can think about this. This is the low energy. N tells us about energy. 1 is the smallest number we can have. It's our lowest energy. Nature always wants to go to our lowest energy. So what we're going to do here is start filling in our electrons from here. So over in, for example, in our multi-electron, I could put 1 here. And then when I have a second, maybe for helium, I would put it like that. That would satisfy all 3 of the principles that we talked about on the previous slides. Now, when we go up to n equals 2, this is where the 2 diagrams are different. So, for example, over in the hydrogen, we see that the 2s and the 2p energy levels are identical in energy. They have the same energy level. So if we were putting in electrons here, we would have some choices to make. But we won't worry about that case at this point because it's just a 1 electron system. It's weird. What we're going to care about is over here in a multi-electron system, where now we see that the 2s is slightly lower energy than the 2p. So as we're adding in electrons, we'd put 1 here, second one here, third, fourth. All right. As we go higher and higher, things get more and more complicated. So for 1 electron cases, 3s, 3p, 3d, they're all the same in terms of energetics. But when we look at a multi-electron system, we see it's very much different now. 3s, 3p, 3d are all increasing across this way. But notice that we have the 4s sandwiched in here. So this is where our pattern kind of has to be a little bit funky. But that's what we're doing here, is we're building an energy, our electrons in according to the lowest energy. So as we're filling in electrons, 3s followed by 3p, followed by 4s, followed by 3d, just because they're filling in terms of electron energies. So what that leads us to is a final configuration that we would have is we're going to start with 1s to 2s to 2p to 3s to 3p to 4s back to 3d to 4p, 5s down to 4d to 5p, 5s, 5d. This is where things get a little bit squidgy. 4f and 5d are similar in energy, but generically we're going to say the F fills after the D and then go back to P after that. So this is that kind of plot that you've seen before. This is our electron configuration ordering that we've seen in general chemistry. Nothing is changing here. We're just now making the recognition of why this happened is that the D is lower in energy than the P that we have here. That's why it is. We see that when we're thinking about in terms of energy sets from n equals, the 3D is much higher than 3s, 3p. It's very high. It's higher than the 4s. That's all we're saying here. Now, just like anything else, we're going to find some exceptions to the rules, and here are the exceptions that you need to really know. There are a total of 6 exceptions, and you'll notice they are all from the D block. They are all transition metals of some sort, but they follow a pattern. So, if we look at copper, silver, and gold, what we would notice is we would expect them to be 3D9 series, is what we would expect them to have. But this is where things get a little bit funky, because remember, what we're trying to do is lower the overall energy of the system. And what we find out, for example, for copper, instead of 3D9, we see that it has pulled one of these s electrons into that d orbital so that we end up with a final configuration of 3d10, 4s1. The reason for this is now I have my d orbitals that I'm looking at here, and if I go ahead and just fill them with 9, I have one lone electron that's missing here. What we find out is if we move an electron into this space, this is actually more stable. This has to do with symmetry of the orbitals, which we're going to talk about later in this semester. But for right now, we just have to know that a full d orbital is exceptionally stable. Same thing is true about a half full d orbital. So in other words, 4 electrons is okay. But if I add a 5th one, let's change that and let's do that in blue. If I have 5 electrons, we find that that's much more stable as a system. And that is what we see in some other cases. For example, when we look at chromium and molybdenum on this list, that's what we see happening here. There is one that's really kind of a pain in the butt here, and that is for palladium. And we see that in this case, it actually takes both of those 5s electrons to give us a complete 4d. These are the only real exceptions that we're going to worry about. If you really look into the literature, sure enough, there's a lot more exceptions to this. Specifically, if we're looking down in the F block, there's all sorts of exceptions. For right now, these are the 6 that you need to know. 3 of them are D9s, 2 of them are D4s, and 1 is a D8. So those are the ones you have to remember for the exceptions. And yeah, admittedly, it's kind of a pain in the butt here to remember that in terms of just a pattern. But remember, it's about energy. Those levels, as we start populating, they start shifting around, and therefore we get a little bit of a deviation in those specific species here. So a little bit awkward, a little bit weird, but definitely meaningful in how we are going to think about their chemistry. So keep those into your head. If you have questions on them, let me know. I'll help you out however I can, as always. And until next time, be excellent to each other.